So let us continue doing some more problems on problems and results on factor groups. The first problem we are going to try today is this. Let H be a subgroup of a finite group G such that the order of G by the order of H is equal to 2, or G of H is equal to 2. Then H is normal. So this means that the number of left or right corsets of H in G is 2. So what we need to prove is that AH is equal to HA for all A in G. This is what we need to prove. We need to show this. Now, let A belongs to G, and that implies A belongs to either H or A belongs to G minus H. So this implies, or if A belongs to H, then AH is equal to HA. No problem, because it is in H. If A belongs to G minus H, then also AH is equal to HA, because HA is equal to G minus H, then that is equal to AH. And A belongs to G minus H, and that implies HA is equal to AH, and that implies H is normal. Next, what we are going to show is the converse of Lagrange's theorem is not always true. Let us state the Lagrange's theorem first. Lagrange theorem. It states that if H is a finite, if a subgroup of, if H is a subgroup of a finite group G, then order of H divides order of G. That is what the Lagrange's theorem is. That is what Lagrange's theorem states. This is always true, but the converse is not true. Meaning, the converse statement will be like this. So, what we are going to prove is there exist finite groups of order n such that there are no subgroups of an order that divides Meaning if G is an order of 24, then 6 is a divisor of 24, we can find a group such that there is no subgroup of order 6 of G. If there is a subgroup H of G, then the Lagrange's theorem states that the order of H divides H. But that does not mean that for every divisor of the order of group there exists a subgroup. So we are going to find a counter example to show this. So what we are going to start is let A4 be the alternating group of the symmetric group on 4 elements. Then A4 contains 4 factorial by 2 elements, that is 12 elements. Now what we are going to prove is there exists no subgroup of A4 of order 6. So we will show that there exists no subgroup of A4 of order 6. So we'll assume HB a subgroup of A4 with order 6. So since A4 divided by order of A4 divided by order of H is equal to 2, from the previous result H is normal. And A4 over H, the factor group of A4 over H, is isomorphic to Z2. Because this contains only 2 elements, so any group of 2 elements is always isomorphic to Z2. And this implies that an element of the square of any element here is always the identity. Z2 is like this: 0, 1, 0, 1, 0, 1, 1, 0. This is Z2. The square of any element, there are 2 elements here, square of this is 0, square of this is 0, the identity. So any element here is, the square of any element is here is the identity of this. So that means sigma H, that is the general element of this factor group, square is always equal to the identity of that group. And that implies sigma square H is equal to H. And that implies sigma square belongs to H. So let us find some examples here. The permutation 1, 2, 3 square. 1, 2, 3. The permutation 1, 2, 3 belongs to A4. A4 contains all the even permutations. This is actually 1, 2, 3 is actually written as 1, 2, 1, 3, 1, 2. So this is a product of 2 transpositions, even number of transpositions. So it is actually in A4. So this is actually in A4. So this is actually for all sigma in A4. So this is an 1, 2, 3 belongs to A4 implies this also belongs to, H, because sigma square belongs to H for all, and that implies this is nothing but 132. So 132 belongs to H. And if you take another example, 132 square is equal to 123, that also belongs to H. Similarly, 124 belongs to H, 142 belongs to H, then 134 belongs to H, 143 belongs to H, then 234 belongs to H, then 243 belongs to H. So we clearly found 8 elements in H. So this implies H contains 8 elements. And that is a contradiction because H contains only 6 elements. This is a contradiction, and that implies A4 does not have a subgroup of order 6. Our next problem is every factor groups of a cyclic group is cyclic. So let G be a cyclic group. And that implies G is equal to the group generated by an element for some A belongs to G. So let H be a normal subgroup of G. That means G of H is a factor group. And the claim is G of H is generated by H. That is because when we take the powers of A, we get all elements of G. So that implies the powers of AH runs through all cosets of H in G. And that implies G over H is equal to H. So if you take an example, let's take Z6. Let us take Z6, and Z6 is 0, 1, 2, 3, 4, 5. Because it's a cyclic group, any subgroup of C6 are normal. Let us take H is equal to 0, 3. Okay, so this is a normal subgroup of C6, and C6 is equal to the group generated by 1. So what we need to prove that the cosets of Z over H, that is the factor group C over Z6 over H is equal to H1 plus H 2 plus H. So this is the elements of the factor group. So this is actually generated by 1 plus H. Why? Because 1 plus H, 1 plus H square, 1 plus H cube. This is 1 plus H. This is 1 plus H plus 1 plus H, 2 plus H. This is 1 plus H plus 1 plus H plus 1 plus H, and that is H. And that is exactly what this one is. See, the number of elements in the factor group may differ. See, for example, if you take another subgroup, let us say H1, 0, 2, 4, still the factor group is generated by 1 plus H. So here Z6 over H1 is H1 plus H1 comma 1 plus H1. This also is generated by 1 plus H1. Now let us define a special group called the simple group. Simple group. These are important when you study the series of groups. A non-trivial group, non-trivial in the sense that it has got more than one element. A non-trivial subgroup, a non-trivial group is simple if it does not have any non-trivial proper normal subgroup. Meaning we don't want to consider just 0 as a subgroup of G or the E as a subgroup of the non-trivial group. So it has to be a proper subgroup, and it should not be a trivial subgroup, and it has to be a normal. If there is no such subgroups, then that group is simple. So our next attempt is to find the examples of simple groups. So let us see one example of a simple group. So An is the alternating subgroup of the symmetric group with n elements. See, this An is simple if n is greater than or equal to 5. For all n greater than 5, An is a simple group, meaning An does not have a normal, proper normal subgroup. So to start with the proof of this, we have to follow some steps. So what I'm going to do, I'm going to write down the layout of the proof here, and we'll prove one by one. So the first step to prove this one is every 3 cycles are even. 3 cycles means a cycle with 3 elements, or even means even permutation, meaning this can be written as a product of even number of permutations. The second one is every element of an can be expressed as a product of three cycles. And the third meaning, if you take an even permutation, it can be expressed as a product of 3 cycles. Third step is an is generated by the special 3 cycles R, S, I, where R and S are fixed and 1 less than I less than or equal to n. Meaning you take 2 fixed integers from 1 to n. So these 2 are fixed. This is the variable. So you have n minus 2i's. Then any element of an can be written as a product of the special 3 cycles. The fourth step is if n is a normal subgroup and n contains a 3 cycle, then n is equal to n. See, any 3 cycle is an even permutation, so it is an element of an. But that does not mean that it is an element of n. But if n contains such a 3 cycle, 3 cycle means there's just one 3 cycle. If n contains just one 3 cycle, then n is equal to n. And the last step is every normal subgroup of an contains a 3 cycle. If it contains a 3 cycle, then it is an. And this says that every normal subgroup of an contains a 3 cycle. That means every normal subgroup of an is, if n is any subgroup of normal subgroup of an, then they are same. So this means that an does not contain a proper normal subgroup. If it contains a 3 cycles, it's already an. And n contains always a 3 cycle. So these are the steps that we are going to follow to prove this. So let us start with the first one. Every 3 cycle is even. So let A1, A2, A3 be a 3 cycle. Definitely this can be written as A1, A3, A1, A2, and because it's a product of 2 transposition, it definitely is n. So A1, A2, A3 is a even permutation. That is very simple. Second one, every element of An can be expressed as a product of 3 cycles. See, if sigma belongs to An, that implies sigma is a even permutation. Because An contains only even permutations. That means sigma is equal to A1, A2, A3, A4. I'm going to write it as A2R minus 1, A2R, just to make sure that you have even number of transpositions. So what you do is you take 2 permutations at a time so that it will not leave you another permutation at the end. So this is going to be 2. Yeah. So if you take this, this is actually going to be 2R plus 1, so that it is even. Take 2 at a time so that you don't leave anything behind if you take the last one. So these 2 transpositions can be one of these, A comma B, C comma D, where A, B, C and D are different. A comma B, A comma D, where one of them is common, and A comma B, A comma B, where both of them are same. There is no other way of writing 2 transpositions. Remember, A comma B is equal to B comma A. So you are not taking the reverse order because they are same. Transposition in the reverse. See, this is, if you compute, this is going to be A, C, B, A, C, D. When you compute this one, you will get this. I'm not going to do the computation. You can verify that. So this is going to be A comma D comma B. And this is actually going to be I. Okay. So you can write this as a product of 2 3 cycles or as 3 cycles, and you can disregard this because it doesn't make any sense. If you can cancel this out, so this is not valid. Valid in the sense you can in this product, if it comes A comma B, you can take it out. You don't need that. Those 2 you can take it out. So that means any product of 2 transpositions can be written as a product of 3 cycles. Either it is a 3 cycle or a product of 3 cycles. So that means sigma can be expressed as a product of 3 cycles. So we are coming to the third step. In the third step, what we need to prove is, we have already proven that every element of An can be expressed as 3 cycles. But these 3 cycles are not, any 3 cycles are not in this form. There are different types of 3 cycles. We need to express every element of An as a product of special 3 cycles, in which first 2 are all constant. R and S are fixed here. So let us list out all the different kinds of 3 cycles. The kinds of 3 cycles are R, S, I, then you can say RIS, then you can say we'll drop S out, so RIJ, we'll drop R out, so IJ, then we can write it as we'll drop both R and S, so IJK. See, these are not, only this one is the special 3 cycle. These 4 are not special 3 cycles. So we need to express these 4 as a product of special 3 cycles. So this is already a special 3 cycle. This we can write it as RSI square. This we can write it as RSJ RSI square. This we can write it as RSJ square RSI. This we can write it as RSI square RSK RSJ square RSI. So we are expressing any kinds of 3 cycles in terms of products of special 3 cycles. In the left hand side, every 3 cycles starts with R and S. So this implies sigma belongs to An, implies sigma can be, or you can say An is generated by special 3 cycles RSI, where 1 less than or equal to I less than or equal to N, and I different from R and S, because if I is one of this, then there doesn't have any meaning. Now we need to prove the 4th step. If N is a normal subgroup and N contains 1 3 cycle, then N is equal to An. The way we are going to prove is that if N contains a 3 cycle, N contains all the special 3 cycles, which means that N is equal to N, because N is generated by special 3 cycles. So let us assume that 1 3 cycles, and we'll call it as RSI. We are going to take the first 2 elements of the 3 cycle which belongs to S as the fixed one. Assume that this belongs to N. If this is in N, so what we'll do is we'll fix these 2, and we'll see that every i's 1, 2, 3, etc. up to j, all are belong to this. See here, see that N is normal, which means that G inverse belongs to N for all N belongs to N and G belongs to G. This is the necessary and sufficient condition for a subgroup to be normal. So let us take, so this already belongs to N. So we are going to replace this N with this. But the G is R comma S, I comma J belongs to An, because it's a product of 2 transpositions. So this implies that RS IJ, this is our G, and our N is R S I, this is our n, and G inverse is R comma S I comma J inverse. If you compute this one, you are going to get R S J. I'm not going to do the computation here. I will leave it to you as an exercise. So this definitely belongs to n. That means if RSI belongs to n, RSJ belongs to n for all j between 1 and n. That means n contains all special 3 cycles with the R and S as fixed, and that implies n is equal to n. The fifth step is done in, again, 3 multiple sub-steps. See, every element of n can be expressed as a product of 3 cycles, right? So, if sigma belongs to n, that implies sigma is equal to A1, A2, A3, A4, A5, dash dash, sorry, A6, dash dash, some 3 cycles here. Because every even permutation can be written like this. There are lots of disjoint cycles, or there are lots of cycles where there are common elements. So, there are 3 ways you can write this as disjoint cycles. One is you will have A1 dash dash AR where R is greater than 3 and a permutation. This can be probably identity permutation. No problem. But you can see what I'm trying to say is if you have common elements here, you can really expand this one to a 4 or 5 or 6 or 7 cycles, so that you can create a disjoint cycles. What we need to do first is you take the disjoint cycles on one side and the cycles with the common elements on the another side and trying to expand this. So you'll get a very long cycle and another cycle which is disjoint from here. That means mu does not contain any of this R. Next one will be mu of A4, A5, A6, A1, A2, A3. 2 different 3 cycles. And the third one will be A1, A2, A3. These are the only possible ways of writing, expressing an element in n or even an. And there is one more, mu of A1, A2, A3, A4. But this is already, you know that this can be either expressed as this or expressed as this. We already know from here. So, what we are trying to prove is if n is this, if n is this, n is if sigma is in this form, then we can find a 3 cycle in n. Or if it is in this form also, we can find, and if this form also you can find. And that is the next step. So, let sigma belongs to n. If sigma equals mu times a1 dash ar or greater than 3, then n contains a 3 cycle. That is for 5.1. 5.2 is if sigma is equal to mu of a4, a5, a6, a1, a2, a3, then n contains a 3 cycle. 5.3 is if sigma is equal to mu of a1, a2, a3, then n contains a 3 cycle. So that is what we are going to prove here. So let us take the first one, 5.1. Sigma equals mu times a1 dash ar or greater than 3. And this belongs to n. We'll write it like this. This belongs to n or greater than 3. That is assumption. And one more assumption is n is normal. This implies sigma inverse belongs to n because it's a group, subgroup. So its inverse has to be there. And we are going to assume the same thing like G and G inverse belongs to n, where G and G belongs for all G in G and n in n, right? So we are going to take G as A1, A2, A3. These three are already there because R is greater than 3. So definitely this will be there. This times sigma inverse, sigma times A1, A2, A3 inverse belongs to n. Now you compute these two. Sigma inverse of A1, A2, A3, sigma A1, A2, A3 inverse also belongs to n. And when you compute this one, this is going to be A1, A3, AR. That belongs to n. That implies n contains a 3 cycle. Now let us prove the second part, 5.2. Here sigma equals mu of A4, A5, A6, A1, A2, A3. In this case, what we are going to compute is sigma inverse, then A1, A2, A4 times sigma times A1, A2, A4 inverse. and that belongs to n. This belongs to n. So this, because n is normal, this belongs to n. And that implies this is actually equal to A1, A4, A2, A3, A6, and that belongs to n. And if this belongs to n, we know that from the previous step, if this is a cycle of 1, 2, 3, 4, 5, it's greater than 3. So if you are using the 5.1, this implies that n is equal to a. Because n contains, or we can say from 5.1, n contains A3 cycle. And the last one is 5.3. Sigma is equal to mu of A1, A2, A3. In here, it is simple sigma square. If you compute, that is going to be A1, A3, A2. And that belongs to n. So that means n contains A3 cycle. Because if sigma belongs to n, sigma square also belongs to n. And when you compute, that is actually mu of A1, A2, A3 square. If you compute, then you are going to get this. So what we have proved is every normal subgroup of An contains a 3 cycle. And if that subgroup contains a 3 cycle, n is equal to An. And if n is a normal subgroup of An, proper normal subgroup of An, then it cannot be a proper subgroup because it contains a 3 cycle, and that means An is simple. So what we are arriving at is, if n is a non-trivial normal subgroup of An, then n contains a 3 cycle, and that implies n is equal to An, and that implies An does not have a proper normal non-trivial subgroup, and that implies An is